Hello, you wonderful Earth Science kids. Today we're going to be going over the Daily Planet, Chapter 1, Number 2, where we're going to be learning about latitude and longitude. All right, so I highly recommend that you have your daily out with you so that you could be going over this with us. The first page, we have to go over just reading it and filling it in and trying to understand latitude and longitude that way. And then we'll get into filling in the back page. Okay? So on this first page, as we're working on this, the lesson there, it says to find your position in a large rectangular room, we'll need to mark off a set of lines between two walls. So we would mark off lines between two walls much like this. Okay. Now you could stand anywhere along this line and you'd be able to indicate what line you're on. But how do you designate a point along the line? Well, easy. Just make a series of lines going perpendicular to the first set. So these lines are now perpendicular to the first set. So how do you designate a point? So where the two lines cross would be a point. For example, right there would be a point. All right, so if you label each line so it's different from all the other lines, you can indicate with a set of coordinates exactly where your point is. So what would the coordinates of this point be? Well, if we were labeling A, B, C, D, E, and so on, and then we labeled across the top 1, 2, 3, 4, 5, and so on, we would see that our coordinates would be, well, if they would like horizontal first, then vertical, we would see our coordinates would be C3. That makes sense. So any point on a flat surface can be determined in this manner. But how would we apply this method to the spherical surface of the Earth? After all, locating where you are going on the planet is a matter of utmost importance to nearly everyone at some time or another. We need reference points on the Earth to attach these lines to. There are 3 natural reference points on the Earth, all having to do with the rotation of the Earth. The north and south poles are where the axis of rotation meets the surface. The equator is the. So now, how do we do this on a globe? Well, a globe, nice circle like that, we have these 3 reference points. North Pole, South Pole, and the equator. So lines of latitude naturally stem from the equator. They are parallel with the equator. They never touch, and they measure north and south, degrees north and south of the equator. From the equatorial line, this dark line I'll make here, the dark line. From the equatorial line, you could go 90 degrees north, or you could go up to 90 degrees south. These are not really lines, they are circles. If you imagine a 3-dimensional sphere, these are circles going around, and the circles of latitude never ever touch. So longitude lines now, longitude lines proceed from the North Pole to the South Pole, or South Pole to the North Pole. And they show degrees east and west of a line that we have to draw on the Earth that would be known as the prime meridian. Now, this is not a natural point on the Earth. This is rather a point we picked to represent 0 on the Earth. There are no natural longitude lines that you could identify on the Earth. So longitude, we have to determine from just dividing the circle up into 360 degrees going around. But in practice, we go from the prime meridian line, from whichever line we designate as the prime meridian line. Right now we are going degrees east and west of the prime meridian. So if we are going east and west, We could go all the way around the planet up to 180 degrees east, or 180 degrees wouldn't have a measure, but you could get 180 degrees east measurement and 180 degrees west measurement. Where they meet would be the 180-degree longitude line. So latitude, the maximum is 90 degrees north or south. Longitude, maximum is 180 degrees east or west. So this is the basic idea of latitude and longitude. Using this method, we can identify absolutely any place on the globe. That's pretty good. We need to be able to identify your exact location on the globe. Many of you have GPSs in your car, and on your phone for that matter. Your GPS can locate with extreme precision your exact spot on the globe. And the really neat thing is the numbers it gives out for latitude and longitude represent one and only one exact spot on the globe. And it represents exactly where you're standing. If we look at the polar views of the Earth, in other words, the views from above the Earth or below the Earth, the North Pole and the South Pole being centered in our globe then, just consider which hemisphere has the most surface covered by water. You don't have to look very long to realize it's the southern hemisphere. So now, if you would, please draw a circle on your daily with the North and South poles labeled. Show the prime meridian and the equator. Draw and label North and South latitude and East and West longitude lines. Right? Some good practice. You have to be able to do this. So if we draw a circle, what's that line going to be called and labeled? Right, that's the equator. And if I draw a line going from North Pole to South Pole, and I say it's the primary line, what do you call it? Well, that would be the prime meridian, this line going from North Pole to South Pole. So that would be the prime meridian. And this object up here is the North Pole. This object down here is the South Pole. And then if we draw and label North and South latitude lines, these are your latitude. Notice, they never touch. One of the ways we remember that is the old earth science statement, latitude is flatitude. You can use that if you'd like. Longitude lines are not parallel. They have to touch at the north and south poles. So your longitude lines then go on the globe like that. Now, if you look at a polar graph of the Earth, this would be looking from the North Pole or the South Pole. Label the equator. Which line would be the equator here? It's kind of confusing when you're looking down on the globe, but I hope you could see it would be the outermost line here. The outermost line must be the equator. Label the North Pole. Well, the very center of this would be the North Pole. So notice the world map. Now, note the lines of longitude do not touch at the poles. Okay, we've exaggerated this map because, well, it's not a sphere. So we have to pull it out. And by doing it like this and not having the lines touch at the north and south poles, perhaps you can see that objects like Greenland are ridiculously huge compared to their actual size. Way up in the north part of the world and also way down in the southern part of the world, we see ridiculous exaggerations. That's because of the way this map is set up. So the distortion at high latitudes is just because the longitude lines are not touching at the north and south poles. So they're more spread apart than would normally be. Okay, here you can see how we think of longitude. It actually makes an angle with the center of the Earth, and that's how we would measure the longitude. That actual angle right there would be how far you are from the prime meridian. Okay, so these are the longitude lines then, and notice how they arc across the Earth and they all touch at the North and the South poles. That means that the distance between longitude lines varies. At the equator, you have a larger distance between longitude lines than you'd have at the poles. Indeed, at the poles, in fact, you could be standing in a place where you're standing on all the longitude lines at the same time. So we split the measurement of the Earth into degrees, minutes, and seconds. The Earth's circumference at the equator is 40,076 kilometers. Well, this is divided over 360 degrees. How many kilometers per degree? Look at that, 111 kilometers for every degree. So clearly, we need a way to break the degrees up into smaller units. So, using old-style counting, we break each degree up into 60 minutes, just like an hour is broken into 60 minutes. So each degree is broken into 60 minutes. But if you divide 111 kilometers into 60, you'll still be getting nearly 2 kilometers per minute. We need to break it up even more. So each minute is broken into 60 seconds. And that truly makes a small quantity that designates a point on planet Earth pretty easily. So when we're navigating on planet Earth, well, it depends really on finding two different things: the movement north and south and the movement east and west. And how do you do each of these? Well, the north and south movement, that's not really so hard. Movement to the north and south can easily be determined by the changes in the position of Polaris, or the North Star. Your latitude in the northern hemisphere is equal to the elevation of Polaris above the horizon. So that's easy. There's no calculation. If Polaris is 10 degrees above your horizon, your latitude, excellent, 10 degrees. If we're located at 42 degrees north latitude, which is correct, how high in the sky for us is Polaris? 42 degrees. Excellent. When you're standing at the North Pole, where do you have to look to see Polaris? You'd look straight up, or 90 degrees above you. What's the latitude of the North Pole? 90 degrees. Okay. So if you're traveling on a ship and find that Polaris is getting lower in the sky every night, which way are you moving? Well, you're getting further away from the place where Polaris would be directly overhead. That would be the North Pole. If you're getting further away from there, you must be moving south. If you're on a ship traveling and you find that Polaris is getting higher in the sky every night, you must be moving, hope you got, north. How do you find Polaris? Good question. Well, most of us know the Big Dipper in the sky, right? So if you know the Big Dipper in the sky, you also know that you can use, well, maybe you know, that these two stars down in the end cup are the pointer stars, and they point directly to the North Star. So using these, you can see where the North Star is. This other constellation here is Cassiopeia, and Cassiopeia generally points, the open part of the W points towards the pole star, the North Star, as well. But the easiest thing to use is the Big Dipper, because the two stars here really do very nicely point right to the North Star. Now, surprisingly enough, many people think the North Star is the brightest star in the sky, and no, it is not anywhere near the brightest star in the sky, but it is the brightest star in this general region of the sky. So if you use the Big Dipper and count about 4 times the distance between the two pointer stars, you'll get to the North Star. So if we look at this person standing here, it makes you wonder, okay, is it 47 degrees their latitude, or is their latitude 43 degrees? Now, this is how the Regents is going to pose it. They're not going to tell you what you're supposed to know. They're going to give you some choices. So the question is your latitude Polaris's declination beneath the zenith, or is it your elevation above the horizon? Well, if you remember what we were saying, your latitude is the elevation of Polaris above the horizon. So this gentleman's latitude would be 43 degrees. How would we measure east and west movement? Well, the Earth rotates once every 24 hours. One turn is equal to 360 degrees. So how many degrees does the Earth turn every hour? If you divide 360 degrees by 24 hours, you'll come up with 15 degrees per hour. So that is how fast we turn. So this means if the sun reaches local solar noon 1 hour earlier than usual, you have moved east. Well, how many degrees? If you moved in such a way as to get east, you're moving east, and you moved in such a way as to get the sun to rise 1 hour earlier, you moved, how far? Can you get it? Yes, you moved east 15 degrees. 15 degrees. So if the sun reaches local solar noon 1 hour later than usual, well, you're racing away from the sun. So you must be moving west, and you've moved west 15 degrees. So that's not so hard. Thanks for watching.